Yes, so I did open it up after I got your email.
Oh, okay.
So today we're actually, as a quiz, we're going to just do a homework problem
Oh,
in class together. I have to remind Chris not to turn this off. That color printer is kind of quirky, and so yesterday evening it started printing these,
Oh, there we go.
yeah, slides that I printed. Yeah. So this will help when we're working through the integration type problems. And it printed some of these.
Thank you.
And the other thing that I got up and going here is this. Okay, so this is just a schedule of what I think we will be covering. So as far as these topics, they might, shift a bit, but we probably will have the test on the 28th. Okay, so we'll just kind of adjust either what's the test covers or speed up things as we're working through it. So the main three things here are the three test dates. And of course the final exam is also set. Did I send it down that road?
no, I have one that did.
Okay. Need another one?
I think they need something.
Oh, some of those, yes. Then, as I said, I couldn't get the color printer to go, so sorry you guys have non-color printer ones. There you go. Andrew, were you having trouble getting on? Was it one other person also was having trouble getting on the, so I'll
Yeah.
call after class. I've got a 2-hour break there. There. Okay, so I guess when this gets up and going, we'll maybe do a few more slides and then start in on these. Should we go? Yeah, here it goes. Start in on these particular problems here. So, as I said, the PowerPoint slides, 86 of them, so they are good, but I won't be talking in detail about each and every one of them. So my computer is still getting up and going here. So the first set of kinematics equations that we cover are a is equal to dx dt and a is equal to dv dt. Okay, and then the combination of these two is that a is equal to v dv dx. Okay, you could rearrange those to get that one. So the simplest problem, which is one that you will not have on a test, and I think you maybe have one homework like it, would be to be given x as a function of time, and then asked to find the velocity and, in this case, the time, the position, and acceleration of the particle when v is equal to 0. So these basic equations actually are the ones I just wrote up here. So dx dt, dv dt, and v dv dx. I forgot I had a spot down here for them. Okay. So go ahead and take the derivatives and then we can check. Let me get up and going here. All right, so hopefully you were able to differentiate those two and get the same thing. And just I'm trying to print as I said, the color printer I was hoping would cooperate, but it's not. Let's see. Okay, so how did you do with the differentiation? Okay, good. So now we want to know the time, velocity, or time, position, and acceleration when v is equal to 0. So we just take that equation that we got for velocity, and we set it equal to 0. And this just ends up being a factor. You can factor this out. And this is like t minus 2 and t minus 1. Remember that back from middle school, right? And so t is either equal to 2 seconds or 1 second. So there are actually 2 times at which the acceleration is equal to 0, the velocity is equal to 0. And so at 1 second, you can just plug these in. So it would be, plug in a second everywhere you see a t. And you get 15 feet, and then it would be equal to, acceleration would be 12 times the time of 1 second, minus 18, and so it would be equal to 6. Okay, so you have this 0 velocity, but you still have an acceleration. Okay, and then we would do the same thing for the 2 seconds. We would get, at 2 seconds, x is equal to 14 feet, and acceleration is equal to a positive 6 feet per second. There's a unit missing here, it should be seconds squared, feet per second squared. So not bad, right?
Mm-hmm.
So let's see what we have PowerPoint-wise. So you actually have a homework problem similar to this, but sometimes, I guess what I was kind of getting at is that sometimes you are not given acceleration as a function of, or position as a function of time, but rather acceleration as a function of something else. In this case, this particular, let's see, this problem, go here. Okay. So in this particular case, acceleration was given as a function of velocity. And so we have to integrate, but we can't integrate with respect to time. We have to integrate with respect to x and v, so in some cases. So sometimes it's not quite that straightforward. So let's see, on the next example here, I actually wrote it out for you. So let's talk through it and see what you have to do. I also put kind of some detail here as far as what you're going to do. So in these problems, in this case, acceleration is a function of time. So that's kind of nice because we're used to acceleration and velocity and position being functions of time. They said, for example, in the problem statement, it said acceleration is directly proportional to time. If it said it was equal to time, it would just be a is equal to t. But if it was directly proportional to it, we had to multiply time times a constant, and we just called that k. If it said that acceleration was indirectly proportional to time, then it would be k divided by t. Okay? So that's how, they did not give a is equal to k times t, but they just gave some words that allowed you to come up with that relationship. Okay? So they also said there were some boundary conditions in that problem statement, that it started out with a velocity of 400 millimeters per second, and when it was 1 second, it gave the velocity in position. Okay, so 3 different boundary conditions to allow us to solve for 3 different unknowns. Okay, one of the unknowns is the k, that proportionality constant k. The other 2 are the 2 constants of integration once we integrate it twice. Okay, so started out with the basic relationship, substituted in the thing that's different here, substituted in k t for a. Then I took that dt and I put it over on, I put all the t's on one side and all the d's on the other. And so then I integrate it. And that's where we do that kind of not indefinite or definite integration, but the kind of this somewhat in between. So I brought the k out front, and on top of the integral I had the variables t and v. On the bottom I used the boundary condition that at t is equal to 0, velocity was 400 millimeters per second. So I could not use 0 and 370 because those 2 don't match, right? So I have to match the boundary conditions there. I do that simple integration, and once I simplify everything, came up with a velocity as a function of time. Okay. I still had the unknown constant k in there, so this is where I wanted to go ahead and jump in here and figure out what the value of k is. So I've already used up here, I can like mark out that boundary condition. I cannot use that boundary condition again, otherwise I would probably get 0 is equal to 0. So I have to use a brand new boundary condition of the 1 and the 370. So velocity was 370, time was 1, and I came up with the value of k. Okay, so now I had acceleration and velocity only as functions of time. So t was the only unknown in both of those equations, and now that we know what k is equal to. So now I want to figure out the relationship between position and time. So I take my expression for velocity, and so sometimes students will, for example, maybe put velocity is equal to 370 in there, but you can't do that. That's just a boundary condition. It's not the actual equation for velocity. Okay, so you have to jump back, grab that equation for velocity, plug it in, separate it, integrate it, and then in the end we will have this expression for position. So does it look kind of difficult and messy and no thoughts there?
It's like a lot looking at it.
Yeah, it is a lot looking at it, but it's always, the nice thing, it's kind of like statics, you're always doing the same thing. You're substituting in the relationship, integrating once or twice, using boundary conditions, and then, so it's kind of one of those problems that you can do it and get through it and make yourself look really good, but it's not that hard.
Good.
So I thought that maybe, let me log on to the Connect site, and kind of for your quiz today, we will do a 5 minutes. Let's do one more before we do that. Okay. So 11-4, I won't talk about this one in as much detail, but again, on the homework part here, did the exact same thing. The only difference was that we weren't given an unknown constant K. Okay, so we only needed 2 boundary conditions because we integrated twice. So this one was a little bit easier, but if you compare the steps back to the previous problem, it's almost the same. You know, substitute, separate, integrate, and then you do there. Okay, so this one we were finding, again, the time for velocity is equal to 0, and then the position velocity at t is equal to 4 seconds. So does it look less intimidating this second round?
Mm-hmm.
And then I will talk a little bit more in detail about this one. So again, I feel like you can get more from looking at it than you can from copying it. So I just put this on here. You can like highlight things and do different things. So in this one, we were given acceleration as a function of position. So A and X are kind of what we're interested in. Since there's no t there, we probably are going to have to use that third equation of A is equal to v dv dx. Okay. We were given a boundary condition of v is equal to 0.3 when x is equal to 0.4. So we wanted to figure out the maximum velocity. Okay, and that anytime you want, if you want the maximum position, it's when velocity is 0, right? Because of that curve there, it's when your velocity is like changing directions, and it's going to go from positive to negative or negative to positive. That's like the maximum position you are from the equilibrium position. And the same thing with velocity. The maximum velocity is when your acceleration is 0. When your acceleration is going from a positive to a negative, or a negative to the positive, because it's going to speed up, speed up, speed up, and then when A switches its sign, then it's going to start slowing down. The magnitude of it is. So, yeah. So we'll just set A equal to 0 and figure out from there. So we did not want to use any of the equations that involve time. So that's why I used this equation that velocity is equal to, or acceleration is equal to velocity dv dx. And then from there, it's just exactly the same. So we'll bring all the x's on one side, okay, and then we'll bring all the v's on the other side. If acceleration had been 40 minus 160 v, what would we have done with this instead of keeping it on the left-hand side? We would have brought it to the right-hand side with all the other v's. So everything here is x's on the left and like v's on the right. So hopefully on the homework it's some pretty simple integration. I need to go back and check. It's not anything so difficult that you would have to go to an integral table on. Hopefully not. But so this is just direct integration by that power rule. And so do you see how what happens when I put this little bar here? Or do you guys kind of get that? I've done that expression substituting in x, and then I've done that minus that expression substituting in 0.4. And then kind of the same thing here. I had this term with plugging in v, and this term plugging in 0.3. Okay, and what that does then is it basically has the constant of integration fall out into the equation. Okay, so you do not have to add a constant of integration in your equation when you do this kind of hybrid form of integration. We don't have as nice of an equation where v is equal to, this power of x. We could make it v, so v would be equal if we, for whatever reason, had to integrate again in terms of velocity, we could integrate it like that. But we really don't need to do that. The maximum accelerations when, maximum velocities when a is equal to 0. So I just plugged in a is equal to 0 here, solved for x, and then plugged that back into this equation. And then finally, when the velocity was equal to 0, our position was at 0.098 meters, or 0.402 meters. Okay, so let's let you guys practice here for a little bit, and then we'll kind of go back to this. So in assignment 1, we do have some problems that are involving position and velocity and acceleration without time. So on this one, a ball is dropped from a boat so that it strikes the surface of the lake with a speed of 16.5 higher.
Thanks.
16.5 feet per second. While in the water, the ball experiences an acceleration of this. So where a is and b are expressed in feet per second squared, the ball takes 3.3 seconds to reach the bottom of the lake. So we want to figure out the depth of the lake. And then I think, is there another one?
There's another one. Yes.
Oh, okay, yeah, so on the next one, I don't think it'll let me. The next one, the speed of the ball when it hits the bottom of the lake. Round the final answer to 2 decimal places. I'm actually going to let's do this one first. I think we can do it first here. So what I'm going to do is I am going to let you guys think, and this will count as your quiz. So I'm going to let you guys write everything that you know kind of in a problem statement, and let's see if you picked up all of that information. Does that make sense? Okay, so do your given and your required. Let's do this second part here. So we're going to kind of neglect the time here first. Basically here what I want you to do is given, let's can't see that. And required. And kind of write it out so that it's like pieces of information. So your required is going to be velocity when it hits the bottom. will say too that I think downward is in their positive direction. Okay, so we're gonna have downward as being positive.
Hey, Mary, I have a question.
Yes.
So if I the speed like my hits the bottom of the leg beneath to like higher position where the speed is
Yes, and actually, is that what number 1 asked?
yeah,
Okay, so, yeah, you know what, you're right. So we do have to do the first one. We have to find the depth. I was hoping we could just do this one, but. That's all right. So, kind of now going back, we will consider the time there. So kind of what we're working on now is all the given information. Okay, did you get this? So we need to recognize the relationship between A and B, and then the boundary conditions, and X is my vertical distance, and I'm going to consider X equals 0 at the top, and then going down as if it were positive. And then once you get all this, it's just a math problem.
so we'll have a problem like that on the test.
We could, possibly. Actually, we're probably not going to have one that involves linear things, but we will probably have one that involves angular things, which is more of the rigid body part of it as opposed to the particle. Okay. So it will be very similar equations, like we would have to integrate it, but it would be like instead of A, it would be alpha. Instead of B, it would be omega. It would be all those Greek symbols. All right, so we want to figure out the depth here. Okay, so the depth is this unknown here, and we know that it reaches that depth when t is equal to 3.3 seconds. And we also know acceleration here. Okay, so which of these equations involves acceleration, velocity, and time?
A equals to dt.
Yes. So we want to do A is equal to dv dt. And so we have to start with that and come up with an expression for velocity as a function of time. And then once we come up with that, eventually we'll be able to say, oh, v is also equal to dx dt, and then we can solve for x. So first what we're trying to solve for is velocity, and then we're going to use that velocity down here in order to solve for position. So it's kind of that was why I was going to go to part B if we could have, but weren't given enough boundary conditions. Okay, so looking back at the example that I gave you, what do you think we do now?
VDT equal the equation 10 minus.
Yes, good. So where would we put it?
So you put 10 minus 0.8 v.
Good. Okay, so I'm going to let you separate it, and then I'll help you with the integration. Okay, so bring all the v's on one side and all of the t's on another. To get something that looks like that. Okay. So I haven't done something here, and something that I haven't done is I didn't put my upper and lower limits on each. So what should I put up on this one? Good, time, and right here I should put velocity, okay? So I will do that. And then down here, what would I put? And then I would put here, that's good. Okay, so this 1 divided by 10 minus 0.8 v is kind of like a 1 over v. And when you integrate 1 over v dv, it becomes natural log. Okay, so it's actually, the integral of that is natural log of 10 minus 0.8 v divided by, the derivative of negative 0.8 v. So everybody kind of remember how to do that integration by, what is that called? Substitution, I think. Okay. So this would be as hard of an integration as hopefully you will come across. On the test, it will definitely be power rule. So instead of, it would have been like 0.8p or something along those lines, not the 10 minus that. Okay, so now that we do that substitution, this left-hand side becomes, let me let you do it. And then we'll check. Since this is technically still a quiz. 2. So did you get, I just went ahead and put the negative 0.8 to the left and then substituted everything in. And so we are trying to find velocity as a function of time, not time as a function of velocity. So what we would have to do here is we would have to raise both to the power of e. Okay, so this ends up being e to the minus 0.8 t is equal to e raised to the, I guess we would want to actually do we would do this, so natural log of 10 minus 0.8 v minus e to the natural log of 10 minus negative 3.2. So then we can combine terms. Okay, then we can solve for v. All right, what do you think? Do you like using your calculus?
No.
So when we subtract logarithm, then we divide them?
What is that?
Oh, so where you subtract logarithm?
Yeah, so actually I probably wanted to keep it like that. And then I just took e to the everything.
Okay.
Yep. And this makes sense here, the velocity at what is e to the 0? Times t is equal to 0. 1. So at that velocity, it should be, at t is equal to 0, it should be 16